Hi, everyone. Thank you for joining for our second Rockfall Monitoring informational webinar hosted by Will Becker. Will is a technology sales engineer at L.B. Foster with a background in rail technology, including technological research at Norfolk Southern Railroad, and he also has years of experience working with L.B. Foster's technology. If you have any questions during the webinar, please type those in the Q&A chat. You can find that button to the right of the chat button at the top of the screen. All questions will be answered after the presentation. Thank you for joining us. I'll now hand it over to Will.
Chris. I just want to thank everyone for taking the time to join our Rockfall Monitoring informational webinar. This webinar, I'm going to just go over a little bit, a brief overview of how our system works, and then dive into a couple of events and results that we've gotten from our trial period between our system and a slide fence throughout the course of last year. So just to kick off, a brief overview of how Rockfall Monitoring works. When we're looking at the Rockfall monitoring system, the primary um, device that we're using is called our Insight LiDAR. And so the way that that LiDAR system works is we are sending a beam out 100 feet in every direction, and we're doing that 20 times a second and over a 190-degree arc. What you can see in the animation that's playing is about a 5-degree separation of beams. It's actually 20 times that density at 0.25 degrees between the beams. What we'll do is we'll place this LiDAR next to the tracks in a way that allows us to see completely over the tracks. But I think it's important to note that when we're talking about the scan area, there's plenty of areas that we're scanning, you can see in this example here, that we might not be interested in. So for example, here we're seeing this potential rock face over here and a ditch over on the other side. But really, we want to be alarming on obstacles that land in the tracks. So what we do is we take our software and we bound this scan area into what we call our detection zone. And so that detection zone, the way it operates is if an obstacle of a size that it could actually hit your train lands in that detection zone, we're going to send an alarm out on that, and we're going to say where that obstacle was detected in the detection zone so a maintainer can clear that obstacle and resume normal traffic. Part of the safety case that we make internally is that we'll actually want to be seeing this obstacle from multiple LiDARs at the same time. And so what that looks like, you can see that I've added LiDARs to the left and to the right of this main LiDAR, and you get this redundant overlap of scan beams. Now, as I said, the number of beams are actually 20 times the amount that is shown in this image. And so you can imagine that the density of these beams is very tight. Any obstacle that lands in the detection zone, we're seeing from multiple angles and can precisely determine that that obstacle's in the tracks and in our detection zone. So, when we actually deploy this and you look at an actual site, this is what it kind of looks like. You have LiDARs, you can see them here on the right-hand side, and they're deployed down the line with an average spacing of around 90 feet between each LiDAR. And that gives us a pretty comfortable about a 10-foot overlap since they scan 100 feet in either direction. So that's just a really quick and brief overview of how the Rockfall monitoring system works. What I really want to dive into today, since this is our second webinar, is some results from a trial that we did at a major Class 1 railroad and a head-to-head between a slide fence and our Rockfall monitoring system. So before we really get into our system, just for those who may not be aware, I want to detail what a slide fence is and how it works. So when we're looking at a slide fence, there's generally two different types that are out there. There are tension fences, and so these have a high tensile wire that is along the tracks. And when that tension is applied to the wire, let's say a rock falls, it causes tension in these wires. it will cause a mechanical breaker to be tripped, and they know that something potentially has come down and is now caught in the fence. The other is called a break wire fence, and these are somewhat more common. The break wire fences operate in a similar manner, but rather than having the high tensile strength wire, you have a low tensile strength wire. And so what that does is it allows the wires to break when a rock comes through. The reasons for doing this are varied, but generally the idea is that um, you're less likely, if you do have a large event to come down, it's not going to tear down your whole fence, and it can be considered safer. They send a small current through these break wires, and when the wire breaks, you'll get a break in the circuit, and that circuit break is what would indicate that a rock may have fallen through your fence. So I just highlight that because when it comes to rock detection, this slide fence is the industry standard and really hasn't seen any innovation since it's been first implemented. Now, the slide fences in our trial, we had the unique opportunity to look at the results that we were getting from the slide fence. So we had our system next to a slide fence, and over the course of the year, we ended up looking at how much slow order time that these slide fences were accruing. Anytime that a slide fence activates, the trains in the area need to slow to an approach speed. And the reason for that is that when a slide fence activates, the assumption is that something is on the tracks. Now, that may be true, that may not be true, but to keep trains safe, there needs to be a slow order issued, just so trains are operating at a caution and can stop within half the range of sight distance as they approach that slide zone. So, throughout the year at the one fence that we were looking at a major class one, they had 783 hours of slow order time. And I think a good question that you'd have to ask is, how many of those are valid slow orders that were being imposed on the train traffic? So we did an analysis on the alarms that they were getting, and throughout the period, those delay times were caused by 106 alarms. Of those, only one of the 106 alarms were considered a true and valid event. And then on the other side of that, two of the events that were valid events were actually not captured. And so the slide fence only detected one out of three of what we would consider a valid event, which in our opinion is, fairly poor performance when it comes to catching these critical incidents. Just to go back a little bit on a rock slide fence, and one of the real drawbacks in why these 105 events ends up causing your 783 hours of slow order time is that when those wires break, the slide fence is in an alarm condition until someone goes out there and manually repairs the fence. So that involves someone getting out there, generally in fall protection, getting up on these fences. Let's say it's, it could be a wire all the way at the top here that broke. Let's say a small rock has come down and broken one of these wires. And so sometimes it involves bucket trucks, fall protection, and it can take hours and hours, days and days sometimes, for someone qualified to get out there and repair the fence into working order. So now I'm just going to go into a little bit of the missed events that the slide fence missed, and these events were captured in our head-to-head trial by our Rockfall monitoring system. So in this event that we captured, you can see our rockfall monitoring system is here on the right side. And it's hard to tell since it was nighttime, but there are the wires of the slide fence on this far side. And this rock actually ended up being a missed detection by the slide fence, but 45 seconds after this rock came to a stop, our system correctly sent an alarm indication saying that there was a rock that had been detected on the tracks and that trains were required to stop. If we look at the video again, you can actually see that this rock ends up just somehow slipping through the two bottom wires here without breaking them. And so that's what caused the misdetection. And I just want to highlight that because I think the assumption from the industry before we started putting these results together is that a slide fence was adequately sufficient as far as the safety case goes for detecting these types of events, especially boulders of this size. But right here, we're showing that, depending on how the rock comes down the slope, it can sometimes bounce over the fence, it can sometimes slide through under the fence. That because the slide fence isn't directly monitoring the track itself, that you're actually opening yourself up to a level of risk where rockfall monitoring is monitoring the actual tracks. It's going to provide a high level of safety. So looking at this event a little bit further, I just have a second angle here. You're going to see the rocket's going to come down on the far right-hand side. Um, so, pretty large rocket sitting right in the center of the tracks. This would have been a major issue when it came to derailing a train. So our alert did prompt maintenance to come out and remove this rock. Here's a shot of it in the morning, right before it was cleared, with the train shop stopped short ahead of it. So, this is where I think from a safety standpoint, rockfall monitoring is showing that it is safer than a slide fence. And that's before we even consider the operational impacts that rockfall monitoring um, is going to have compared to a slide fence when it comes to false alarms. So looking at a second event that we captured, this is, as I mentioned, there were two events that we captured that we considered true events. And a true event is a rock that falls on the tracks that a train could hit, um, that the slide fence missed. So here's a second event. This is further down at the same site. So you can see that this rock here ends up right next to the tracks. Does get a little bit cloudy here. And once again, this happened to get through the slide fence without being detected by the slide fence, but it was detected once again 45 seconds after it came to a rest by the rockfall monitoring system, and we sent an alarm indication that there was a rock on the tracks. So as I said, we're going to alarm on any rock that a train can hit, and this is probably the minimum detection size that we would reliably alarm upon. You can see that it's just tall enough to get knocked over by a train here, and that's exactly why we're going to alarm on this obstacle. So that kind of covers what I would say the major safety advantage that we're seeing from rockfall monitoring in our early results. When we're looking at the system in true events, the rockfall monitoring system has never missed a valid event. During our trial period, the slide fences have. So right there, we have a substantial safety case that we can start making around rockfall monitoring and its performance. There's another part of the puzzle here, and that's anytime that a slide fence activates, you're going to have some pretty large operational impacts. These false alarms from a slide fence and the fact that you need to go out and physically repair them before you can resume normal train operation results in a lot of slow order time. And so what we did is we tabulated our system and the amount of slow order time that our system was inputting into the signaling system compared to the amount of slow order time that the slide fence was inputting into the signal system. And you can see from this graph that throughout the months of July, August, September, October, where we compiled these results, that we are fractionally less amount of slow order time than what the slide fence is inputting into the signal system. And so the main takeaway here is that with a rockfall monitoring system that is implemented at the railroad instead of a slide fence, you're not only going to garner safety improvements, but you're also going to increase your operating speed, generate network capacity via the velocity improvements that you're going to see. And, at this railroad that we've been working with, this is what really interested them, that they can put this on a fairly congested line and essentially run trains without slow orders through a fairly long section of tracks that has slide fences throughout the whole thing. So we've been doing a lot of work since this trial period and during this trial period. I would say that the trial period was conducted via our Gen 1 system, and we made some upgrades since then. And so I did want to cover those that have made this has made the system even better. Um, so just to go through a couple of them, we've done some work on upgrading our control system, which I'll go over, uh, redesigning the entire system architecture to be more installation friendly, and updating the hardware. So the hardware has been greatly reduced as far as what's needed out at the site. And then finally, if we go back, there are a couple of times, we are still getting some slow order time. And so as part of our continuous improvement, we were looking to do some software upgrades to have new detection algorithms to reduce some of the few false alarms that we're seeing around birds and fog that are contributing to the couple of minutes here and an hour 25 throughout these months from the LiDAR system as compared to the slide fence. And so, we're hoping to get this as close to zero as we possibly can. So the control panel, this is the control panel that was deployed at the trial site. And then our newest version, you can see, have made a lot of changes. Looks a lot different. The main thing that you'd note is that there's an HMI screen at the top. But the other thing that I'd like to point out is that that control panel, when we actually put it next to the other one, it's hard to tell in the pictures, but it is substantially smaller. And the reason that we did that is that we wanted to make sure that you could put these into an existing signal house that may have a lot of equipment in it, and it isn't too onerous. And so, this is really us going from having just a trial site to going to having production sites. And so this is our production hardware that we've rolled out there. When it comes to that HMI, the HMI screen is actually adding a lot of in the signal house functionality. So what you can see here is that you can see all of your LiDAR at the site. This example, the site's 7 LiDAR long. And you can see if they're an alarm or not an alarm. You can see the CCTV camera is properly communicating. Any faults, maintenance notifications, all of that can be found on the HMI screen. The reason why this is nice to have is that we went forward with before we went forward with this, you can kind of see that on the old control panel, there's really no interface. And so this you were having to run a custom piece of software, plug into the control panel, and only then you could see how the system performance is. Now, any signal maintainer that comes in can look at the control panel, see the system status, see any alarms, see any faults. It's much more maintainable from that side. So another added feature and functionality is that on the HMI screen, when we're detecting an alarm, one of the pieces of feedback that we got from our customers is that when you have an alarm, for example, you noticed in that second true alarm, you had a lot of rock pieces fall and they went all over the place. Well, it's not entirely clear in our old iteration which one of those rocks is causing the alarm or if they all are. So when clearing the track, what we've added is this little a graphic that can be used to identify where in relation to the LiDAR that obstacle is that we're alarming on. And from that, you can remove it, make sure that it's showing clear on your HMI screen, and you know that you've removed the obstacle. The One of the biggest advantages to that is that when we're talking about resetting alarms on rockfall monitoring, unlike a slide fence, the way that that's done is by removing the alarming obstacle. Once that obstacle is removed and the track's determined to be clear, the system will automatically go into a clear condition. So as far as other upgrades that we've made, the system architecture has been upgraded substantially from the original installation. And this is once again from feedback from our customers. So first and foremost, the power that we had been using was all AC powered. Um, and the idea there in the past was that AC power potentially could be used for longer runs. But we have modernized our architecture to actually be able to run off of an inherently safe low voltage DC, 100-volt DC power cable out to a trackside junction box. And so what that allows us to do is have substantial battery backup and look into alternative power methods when it comes to running a Rockfall monitoring system. And then alongside that, we're still using our fiber or Ethernet. One thing that you'll note on this top-down is that there's only one trackside junction box. In the past, we had trackside junction boxes at every single LiDAR, and so there's a massive reduction in the amount of hardware that's out there. And then finally, rather than running the power to each and every LiDAR head, that's how it was done before, we're actually running a PoE Ethernet out to each LiDAR unit individually, which helps reduce the installation complexity of the system. So I mentioned the reduction in the LiDAR hardware, and part of that can be seen here. So I'll call your attention to two different things. First of all, our LiDAR housing itself was pretty robust at the time. There's two things going on here. We had a large mechanical shutter on the front of the LiDAR unit itself, and this aperture was quite large. One of the things that we did realize is that the mechanical shutter is something that's carried over from a system that we had at grade crossings. Out on these rockfall monitoring sites, we're not seeing nearly the level of debris that we've been seeing at the grade crossing sites. It's not an active roadway. And that shutter was a failure point that could be removed, and we wouldn't expect to have detrimental effects. So you can see that this housing is a lot sleeker. There's no mechanical shutter that opens and closes in front of the LiDAR unit itself. And so that reduces the complexity, and it will make it easier to maintain as one less component that could fail out in the field. And then the second thing is that each LiDAR had one of these fairly massive junction boxes on the back. And today we do have a little box. This is here on the back of the unit, but it's substantially smaller than the junction box that we've been using in the past. And notably, there's an LED light on the back. And so if a LiDAR is an alarm and you're a maintainer and you're walking down the tracks, if a LiDAR is an alarm, that LED light will light up to show that that is the unit that's an alarm. And the reason for that is that we have sites where potentially you could have a very large number of LiDAR. It might not be as easy as just looking out of the signal house and saying that, it's LiDAR 3 and you can see it, but, you may be talking about having to walk down a mile of track. And so the idea is that any alarming LiDAR is easily identified just from a walk down the tracks. You can see that indicator light. So that covers some of the improvements that we've made. And now I want to move over to the question and answers section. I know I covered a lot here, and I would be interested to hear what if anyone has any questions specifically around the trial results or any questions about how the system operates. And I don't see any questions yet, but if anyone's got anything, feel free to throw them in the chat there. Well, if there are no further questions, then I thank everyone for taking the time to join this webinar, and we'll expect to continue doing some of these throughout the year. Thank you, Meredith, for hosting me today, and I appreciate you all taking the time out of your day to learn a little bit more about rockfall monitoring.
Thanks, Will.
Thank you.